This is an introduction to a simple computing architecture, which otherwise in computer science curriculums is known as computer organization. The purpose here is to introduce the various building blocks that make up a simple computer and how they work together. The architecture of today's computers is much more complex than this, but the major parts and the basic idea of the inner workings is still the same. So this computer consists of a unit that we refer to as the Central Processing Unit, or CPU, that is the heart of the system. And then it has a memory that stores programs and data, and various peripherals such as printers, DVD readers or writers, and anything that you attach to a computer and have it work with it. These represent a bunch of wires that usually carry signals, and some of them are dedicated to carrying data, some of them are dedicated to carrying information that we refer to as address. Let's take a look at the memory to begin with, because that is probably the easiest thing to introduce. This memory here is represented as a single block, whereas in reality it is a whole hierarchy consisting of RAM and maybe hard drives, these days electronic memories or SSDs, and it stores programs, instructions of programs like this that are stored sequentially, and in most of the cases they're supposed to be executed sequentially. The instructions are binary vectors. In other words, they are vectors of zeros and ones that either represent data and numbers or represent information that is for control purposes, to control the hardware of the computer to do certain things. Those codes are referred to as instructions. In other memory locations or other sections of memory, you may have, again, binary vectors that represent just data. A memory usually has a memory address register, or MAR, to which we supply an address, which is a pointer to a specific location in the whole memory, from which we would like to get data that is stored there, or to which we would like to write or store data. There's another register over here, which is called the Memory Data Register, or MDR for short, and this register is supposed to hold data. So if we're trying to read the memory, then we supply an address, a pointer to the data that we would like to retrieve, to the MAR. We also provide a control signal to the memory, because we have to distinguish between read and write operations. So there is a control signal which is not shown here, but it would be a simple control signal specifying whether the operation, the access operation that we're trying to do, is a read or it's a write. So in the case of a read, the contents of the MAR are used to access a particular memory location, and then whatever is contained in that memory location will be written into the memory data register. These registers are nothing but buffers just to hold information steady for as long as it is needed for whatever hardware is connected to the memory to pick up on it. If the operation is a write operation, then the control signal that indicates what kind of access we would like to make is going to be a write signal. And in that case, data will have to be supplied from outside to the memory data register, and a memory address needs to be specified. And then upon receiving the write signal, the memory will write this data into the memory location pointed to by the contents of the MAR. Now, going to the CPU, the central processing unit, it consists of a bunch of registers. All these pieces that are shown here, they are in fact registers. This one here is a counter. This one here is a so-called arithmetic logic unit, or ALU. And here we have a control unit, which is the heart of the CPU. It provides all the control signals to coordinate all this hardware to perform the jobs that they need to perform, or the simple tasks that they need to perform in the appropriate sequence so as to achieve a major goal. Now, let's start with the arithmetic logic unit. There are in fact chips out there that are arithmetic logic units, and they take two operands usually and a control code. The control code specifies the operation that we would like the ALU to perform on the operands that are provided to it. This is a typical ALU chip. Goes by these numbers up here. The 74181, for example, is a very common chip. And if you search on the web for the specification sheet or the data sheet for the ALU, you're going to find something like this that describes its operation. It shows the physical layout of the pins, and it shows what it is capable of. There is a description, of course, and somewhere you're going to find a table that shows how the ALU behaves. So over here on the left side, the designations S0, S1, S2, and S3 indicate the control code that is fed to the ALU. And these columns indicate the specific operation that the ALU will perform on its operands, the operand A and the operand B. F is going to be the output of the ALU, and A and B are going to be the two operands. Now, these two operands are an array of vectors, and the layout indicates how these vectors are arranged on the pins of the ALU. The inputs A0, A1, A2, A3 indicate the 4 bits of the A vector, which is the first argument for the ALU, and B0, B1, B2, and B3 indicate the 4 bits of the B vector, which is the second argument of the ALU. The F outputs are over here and indicate which pins of the chip are in fact outputting the result vector. The control signals S0 through S3 are provided over here. And of course, there may be some other control signals. For example, there is an output over here that is designated as CN. It indicates a carry operation. So if we were to do, say, addition between two binary vectors, we may have a carry. Now, this chip is going to only operate on 4-bit vectors. If you would like to operate on 8-bit vectors, you would have to use two chips like these, and you would have to connect the carry output of one to the carry input of the other. Of course, the carry input of the first one would have to be grounded because it should be 0 since there is no carry for it. Now, searching for data sheets may get you to the data sheet by Fairchild or by Texas Instruments or whatever. They may look a little different, but they contain the same information. So this one over here indicates the chip, again, the same chip, and it indicates the inputs and outputs as A vectors and B vectors and control vectors and outputs. Of course, there may be different types of chips. So for example, this one is a so-called chip with pin legs that you can put on a prototyping board, and this one may be a surface mount that has a little different geometry, but the circuit is the same, and the signals are pretty much the same, and the functions are the same for both. So this is the map for the pins and what they do. And then, of course, you have the specification of what it is that the chip does. This again shows the control signals that are provided to the chip. And these columns here indicate the specific operation that is performed when the particular control codes are issued. The difference between these two columns is simply whether the operands are going to be given as active low or active high. In other words, whether they're going to be provided in the usual high means 1 and low means 0 format, or whether they are inverted or complemented, in which case the logic 1 would be indicated by a 0, and the logic 0 will be indicated by a high volts or 5 volts. So if you have active low operands, which means zeros are represented by high voltage, the 5 volts, then the ALU performs this function, okay? And if you have the normal active high operands, then the ALU will perform these functions. Anyhow, this is just to indicate what an ALU looks like and make you aware that they are available out there as independent chips for which you can find specification sheets to see what it is that they actually do. So that is what this part is. Now, this one requires two operands. The operands will come from registers which hold data. So there is a register over here, and there is a whole bunch of registers here, general purpose registers, and any one of these can be routed to the arithmetic logic unit or multiplexed as an operand to the arithmetic logic unit. But one specific register is usually one of the sources, or if there is only one source, then that will be it. And it is usually the destination for results. We designate that specially as accumulator, or ACC for short. And this will be the special register which will be the first operand for any operation, and it will be also the destination of the results. You see, when the arithmetic logic unit performs an operation, then the result goes back into the accumulator. Now let's explain a couple of things here. So these general purpose registers, as I said earlier, one of them can be multiplexed as input or as one of the arguments, one of the operands that the ALU is going to use. Recalling material from combinational logic design, we can refer to the multiplexers, which take a bunch of inputs, they have one output, and they connect one of these inputs to the output. The input that will be connected to the output is usually selected by a control code that is fed to these special lines, which are for the purpose of controlling the multiplexer. Now imagine that if you have a stack of such multiplexers and you provide this same control code to all of them, then all the stack is going to select the same indexed line to go to its corresponding outputs. So if you have a stack of, say, 5 multiplexers like this, then each one, of course, will have its own separate inputs designated or indexed from 0 to 7 and its own output. But if you provide the same control code, then all of them will select the same indexed input to go to the output. So if this code corresponds to, say, number 2, then input I2 will be selected by each one of the 5 multiplexers to go to its output. So a vector of 5 bits connected to the I2 inputs of each one multiplexer in the stack will go to the 5 outputs of the multiplexers. The reason I'm referring to this is because this is one way that you can envision how a register out of a stack will be picked to be connected to this input of the arithmetic logic unit. So you could very well have a stack of multiplexers over here that will select the appropriate register. In other words, each multiplexer will be selecting one of the bits of the register, and collectively all the multiplexers will select all the bits of that one register to connect it to the inputs of the ALU. Now consider this arrangement of a multiplexer and a demultiplexer, where the output of the multiplexer is connected to the input of the demultiplexer. On the multiplexer side, the ABC code provides a control code to the multiplexer to select one of these inputs to come to the output. On the demultiplexer side, the EFG code determines which output the input is going to be driven to. So imagine that you have different entities producing data on the inputs of the multiplexer, and then again different entities that consume data on the demultiplexer side. With choosing appropriately the controls ABC and EFG, you can select any one of these inputs to be connected to any one of these outputs. So the components that are connected at these inputs and those that are connected on these outputs, they can be connected by simply selecting the ABC and EFG codes appropriately. In other words, any one of these components that are at the inputs of the multiplexer can be connected on demand to any of the components that are at the output of the demultiplexer if you appropriately select the codes A, B, C, and E, F, G. The reason I'm referring to this is because this is one way to understand how different signal paths can dynamically be created in a complex system. This is very simplistic, however, it shows how it is possible to have a bunch of electronics which allow communication between different devices to reconnect these devices at will by using simply control codes. The reason I'm referring to this is to explain how it is possible to have paths dynamically created by just using control codes that are produced somehow. So who is going to produce these control codes? That's going to be the CLU, the Control Logic Unit. This is the one that generates the control signals that control the hardware and also generates the timing signals that orchestrate all this hardware to perform tasks in a coordinated way in order to achieve a certain result. Let's take one very simple example. Let's say that we need to add the contents of the accumulator to one of these general purpose registers, and the result needs to go back to the accumulator. Let's see what tasks need to happen. For one thing, the register that is going to be the second operand has to be selected. That means that some multiplexing device around here should receive the codes to select that particular register to connect to the arithmetic logic unit. So this code is going to be provided by the control logic unit. Then the arithmetic logic unit needs to receive a code that indicates what operation exactly to perform on the two operands that are feeding it. The control logic unit again is going to provide that code to the arithmetic logic unit. And then the result that is produced has to go into the accumulator, which means the accumulator has to receive a load signal in order to load as its content whatever appears at its data inputs. And again, the one that is going to provide this signal is going to be the control logic unit. So this is becoming really important, and we're going to talk about how this one is implemented later on. But for now, we need to see how program instructions that are residing in memory come into the CPU and how then they are processed. This operation follows generally a pattern of two phases. One is the instruction fetch phase, by which the instruction is brought into the CPU from memory, and then the instruction decode and execute phase, in which phase the CPU actually performs the meaning or the directives of that instruction. Now, let's see how all of this happens. First, the instruction fetch. At first, an address has to be sent to the memory to indicate which instruction needs to come into the CPU. That address is provided by the program counter. We're going to talk more about this later. But for now, let's just say that the content of the program counter is used as an address. This address is dropped onto the address bus by the program counter, and through the address bus it travels to the memory address register. The memory will then receive a read signal, which indicates that what we want to do is we want to read the memory as opposed to writing it, and the data of that location that is pointed to by that address will go to the memory data register. Now, if you haven't guessed, the one that produces the read or write signal, the control signal to the memory to perform a read operation or a write operation, is going to be the control logic unit. Now, the data from the memory data register will travel through the data bus with the address sitting at the memory address register. The memory will receive a control signal that indicates whether the operation that we would like it to perform is a read operation or a write operation. So is data going to be read from the memory by some external device, or is data going to be written into the memory? So a control signal called the read-write signal, not shown over here for simplicity, indicates whether the operation is a read or it is a write. And if you haven't guessed it already, the control logic unit is the one that produces it. So upon receiving a read signal, the memory is going to read the contents of this address. So whatever instruction happens to be in that address, in that memory location, will come to the memory data register. And from there, it will travel through the data bus to the instruction register, right here. That completes the instruction fetch cycle. Now, one thing we need to note is that this program counter, it is a counter because after it is used to send its content to the through the address bus to the memory, it will auto-increment. So its contents is going to be one up from what it used to be before. It's very important to remember this because it will make sense soon. Now, the instruction is now in the central processing unit, and it is sitting in this special register that we call the instruction register, or IR for short. Now it will be decoded. The instruction is considered to consist of two major parts. One part of this instruction, a number of bits of this instruction, is known or referred to as the opcode, which stands for operating code or operational code. That part indicates what is the task to be accomplished. The rest of the instruction may be an operand. So for example, the instruction may indicate add 5. The add is the opcode. The 5 is an operand that needs to be used for an operation. So add 5 means add to the current contents of the accumulator the number 5. Whenever the operand is supplied along with the instruction, we call that scheme immediate addressing. Now, the opcode that indicates what task is to be performed is fed into the control logic unit. The CLU will analyze the opcode and it will try to figure out what is to be performed. When it figures out what is to be performed, then it will start issuing control signals to coordinate the hardware, set up the data paths that need to be set up, and then it will issue the control signals to make the operation signified by the opcode happen. So let's take the example where the instruction is simply add 5. Well, the add part will be analyzed by the control logic unit. Then what it will do is it will have to route this part, which is the operand, to this location of the ALU. It may have to transfer it first to one of the general purpose registers, and then from there route it to the input of the ALU. Then it will have to produce the code that would make the arithmetic logic unit perform that specific operation, and then it will have to produce the load signal to the accumulator to load the results back. So these are the tasks that it will do. It will set up data paths, it will provide control codes, and then it will provide signals for the data transfers and the data latching as needed. So all of these are going to be done by the control unit for this specific operation. And that completes the instruction decode and execute cycle. So as we noticed, we had 2 cycles. One was the instruction fetch, where the instruction came from memory and the program counter was used to point to that instruction. After the instruction arrived at the CPU, the program counter was automatically incremented. That constituted the instruction fetch cycle. The instruction execute cycle, actually decode and execute cycle, was simply where the control unit analyzed the opcode and provided all the control signals for the operation that is specified to actually happen. Now, in this very simple example that we referred to, the instruction was specifying the opcode and it also had an operand, the so-called immediate addressing scheme. However, it is often the case that the instruction consists of an opcode, but instead of an operand, it provides a pointer to the operand as opposed to the operand itself. In that case, the instruction execute will require additional references to the memory. Now, why would we want the operand part of the instruction to be a pointer to memory? Well, instead of having the instruction add 5, let's say we have the instruction add x, where x is a variable. Well, if x is a variable, then it will be implemented as a memory location or an area in memory. So during program compilation, the compiler discovers the variables. The variables have been declared to be of certain types, and so the compiler finds space in memory that will be enough to store values for that variable depending on what kind it is, whether, for example, it's a character or it's a double real number or an array and so on. So the compiler, upon compilation, it will form a table that will contain all these variable identifiers, and next to it there will be a pointer to memory pointing to the area in which this variable is stored. So when you say add x, then what has to happen is the value of x has to be obtained. The table will be looked up to see where variable x is located. The variable table then will provide this pointer, and using this pointer we'll go to the memory and locate the area where that variable is stored. Whatever happens to be in that area is considered to be the value of the variable. So if we want to be able to add a variable or to use a variable in the operation of addition, then we need this addressing scheme, which is called direct addressing, because the address part or the operand part of the instruction directly points to the memory location or memory area where the value of that variable is stored. So in the case of add x, what will happen is the control unit will analyze the opcode. It will see that it is an add operation. It will also see that the addressing is such that it requires to bring the operand from memory, and then it will produce the control signals that will multiplex the address part of the instruction onto the address bus, from which the memory will get it and obtain the data that is needed, and the data will come to the memory data register, and through the data bus it will travel back to the CPU, usually to land in one of the general purpose registers or the accumulator. Then the control logic unit will proceed as before to produce the control signals to make the operation specified by the opcode happen. Now, for the purposes of completeness, I should indicate that besides the immediate and the indirect addressing, there is another scheme, yet another scheme of addressing, which is called the indirect addressing. During indirect addressing, here's what happens. There is one more level of abstraction. The address part or the operand part of the instruction indicates a memory location where a pointer to the data actually resides. So the difference between the indirect addressing and the direct addressing is that direct addressing provides directly the location of the data. Indirect addressing provides the location which holds the pointer to the location of the data. Now, this may be necessary in order to carry various more complex operations for the computing system. But for our purposes, it should suffice to understand that the different addressing schemes that are used for the address or operand part of the instruction register to indicate the data are three main ones, and those would be the immediate. The operand is in fact contained right here. The second one is the direct, where the contents of this part indicate the location of the data in memory, and the indirect, where the contents of this part point to the memory location that holds a pointer to the memory location that actually holds the data. Now let's talk about this part, the link registers. These registers are registers that are connected in a special way. They form a so-called stack. So they're connected so that the output of one register is connected to the input of the other register. And the whole stack of them is connected that way, with the one on top feeding the one below it. Now, what happens is that sometimes the normal execution of the program, or the normal sequence of executing a program, needs to change. That is when we have a program jump, as we say. Consider this example where a program has a bunch of instructions which are expected to be executed sequentially, as shown here, but a particular instruction is in fact a call to another subprogram. For example, a call to a function or a subroutine or something of the sort. At this point, when this instruction is fetched, it will indicate the subprogram call, and then the program will have to jump to another section of the memory where this subroutine or subprogram resides. When that routine runs, the last instruction usually is going to be a return. That instruction, what it should cause is the return to the instruction that was normally supposed to be executed after this one. Now that did not happen, and after this instruction we had a jump, and this instruction was executed instead. But upon termination of this subroutine and encountering a return instruction, we need to recover back the location of the instruction that was supposed to be executed. So how does that work? How does that happen? Now recall that when this instruction was brought into the CPU, the program counter was auto-incremented, and now we will be pointing to this memory location. So when this instruction came in, the contents of the program counter were auto-incremented to point to this instruction, which should be executed next, normally. However, this one pointed to a subroutine call, so now this instruction has to be brought in. That means that the program counter must be forced to point to this address instead of this. So the contents of the program counter will have to be overwritten with this address so that this instruction comes in. From there on, the program execution continues normally. The program counter gets auto-incremented every time, and it steps through this program until it encounters the return instruction. The return instruction, what it will do is it will restore the program counter. So when when this instruction came in, the program counter was auto-incremented to point to the next instruction after that, or the next memory location after that. However, the return would cause it to restore this memory location, and so the program will go back to where it left off. So how is that facilitated? That is where these link registers come in. Whenever the program counter needs to be saved, then its content will be pushed onto this stack, which means that the contents of the program counter will be pushed onto this register, and the contents of this register will be pushed onto the next one, and so on. So all of the contents of this register will be pushed down all together to make a space over here for the current contents of the program counter to be stored. Now, let's say we'd have a jump instruction. Let's say that the opcode is jump. Then over here, we have the address where we have to jump to. The control unit will see that it is a jump. So what it will do is it will activate appropriate virtual paths to send this address to the program counter and provide a load signal for it to load this address. But before it does that, it will activate the signals that will move the contents of this stack down, and it will store the contents of the program counter on the top of the stack. Then the program counter can be overwritten. Then the control unit will activate whatever signals are needed to establish a virtual path between this part and the program counter, so that this contents can move over to the program counter, and then the control unit would provide the load signal to the program counter to load the contents of the jump address. From there on, the instruction fetch will proceed as before, but the instruction that will be fetched will be the instruction at the jump location. Now let's say that after this jump, this subroutine was executed, and then a return was encountered. So the program counter's previous contents, must be restored. That is going to happen by popping the stack over here. So when the opcode over here is a return, the control unit will provide signals for the stack to be popped. So the contents of the top register will overwrite the program counter. And of course, all the rest will move one up. By that, the program counter now will contain whatever address it needed in order to go back and resume the operation from where it left off. That is the purpose of these registers that we call link registers. Now you might ask, wouldn't one register be enough? Well, yes, except that in that case you would have to assume that your jumps are never going to exceed one level and that you are never going to have nested jumps. Like this, for example, where you have a jump and then while executing this part, you have another jump. And of course, you might have another jump and another jump. So these are nested jumps. And when you jump once, jump twice, when you return, first you have to return here, then on another return you have to return over here. That is facilitated exactly by this stack of registers. At the top of the stack, it's always going to be the address where you have to go back to because of the most recent jump. In this example, if you have a jump and then another jump, this is the most recent jump. So the first recovery has to recover the most recent jump. Then another return would have to recover this jump. And obviously in the stack, this return address will be deeper than this one. This one will be in the top. So you can have a whole bunch of nested jumps, and all of these, the return addresses will exist in the stack in the appropriate order in which you have to return back to. So that's the purpose of the link registers. Now, here we have 5 registers, and now here the link registers are signified as 5 registers, which would mean that you can do 5 levels of jumps, of nested jumps. But in fact, that limit is artificial because normally in today's computers, these link registers are virtually unlimited. Not because there are so many of them physically, but because the bottom of the stack can overflow into memory, into main memory. And so the number of the link registers that you have over here is no limitation for how many nested jumps you can do. And that is, of course, one other difference between this simple computer and today's computers. So this describes all these parts of the simple computer. Again, today's computers are a lot more sophisticated in that the hardware is a lot more, but the basic operation still remains the same. For example, in today's computers, instead of having just one instruction register, you may have a whole bunch of registers. And instead of bringing one instruction at a time, you bring a whole block. Also, along with bringing regular instructions, you might also bring in other blocks of instructions to which you may have to branch to, and you bring them in just to have them ready in case you need them. So yes, today's computers are having a lot more sophisticated hardware than this, but they basically perform the same process as we explained it here, with the instruction fetch and execute cycle and the communication between the CPU and memory. Now, all of this referred to communication between CPU and memory, but what about communication of CPU and peripherals? The peripherals are not really viewed that much differently than memory is. In fact, in some computer architecture schemes that we call memory mapped I/O schemes, peripherals are indistinguishable from memory as far as the CPU is concerned. So for anyone sitting within the CPU, it does not care whether this is a peripheral or it is a memory location. It accesses it exactly as if it was a memory location. In other computer architecture schemes, the so-called I/O mapped I/O schemes, there is a distinction between memory and peripherals. In that case, peripherals are accessed like memory, but with a distinct read-write signal than that of the memory. So in memory mapped I/O, you have one read-write signal, and memory and peripherals are sharing it to indicate whether they're going to be performing a reading or a writing operation. But in the case of I/O mapped I/O, you have a read-write signal which is dedicated to memory and another read-write signal which is for I/O peripherals. In reality, there isn't really that much difference between the two, because if you consider that you have a extra read-write signal in the case of the I/O mapped I/O, you realize that if you were to use that extra signal as part of the address bus, then one more bit in the address bus doubles the addressable memory space. So in memory mapped I/O, everything is memory, but in I/O mapped I/O, in reality, you cluster the addressable space into a part that is mapped onto memory or the memory hierarchy, RAM, hard disks, SSDs, and so on. And the other part is mapped onto the peripherals. Now let's talk a little bit more about the CPU talking to peripherals. Let's say that this peripheral here is a printer, and the CPU wants to send something to the printer to print. Of course, if it's a whole file, it will send it byte by byte, one by one. But besides the repetitious part, let's see how one byte will be sent to it. So let's say the instruction over here is write to a peripheral whose address is given over here, the contents of the accumulator. How's that going to work? Well, of course, the control unit will analyze this, and it will figure out that what it needs to do is it needs to drop this address onto the address bus, and then drive the accumulator onto the data bus. Now, over here, we have an address decoder. So this little piece of hardware, what it does is it monitors the address bus and analyzes the contents of the address bus. Then it has output lines that go to the various peripherals. So the CPU wants to write to this peripheral the contents of the accumulator. So this one over here contains the address of that peripheral. Through the address bus, will reach the address decoder. The address decoder will figure out that, the CPU wants to talk to this peripheral. So it will activate this signal over here. This signal is an enabling signal or a wake-up signal. It will tell the peripheral, you know what? Whatever is on the data bus is for you. Now, what's on the data bus is whatever the control unit drove the accumulator to drop onto the data bus. So if the peripheral is a printer, by merely the fact that it has been activated, it will do its job. It will take whatever is on the data bus and will print it. And that is basically how the CPU will talk to a peripheral. it will provide the address of the peripheral so that that peripheral can be activated, and it will provide data on the data bus for the peripheral to use. Of course, it will also have to provide a read-write signal, whether it's a memory mapped I/O or I/O mapped I/O. A read-write signal will have to be issued to specify what operation is to take place. If the peripheral is an input device, for example, it should receive a read request as opposed to a write request. And of course, the address decoder will have activated it, and whatever it produces will be driven onto the data bus. And then from the data bus, it will arrive at the accumulator. Whereas a write operation will follow the opposite way, and the contents of the accumulator will be driven onto the data bus, and from the data bus, driven onto the peripheral. So that is the simple way that the CPU communicates with a peripheral. That concludes the simple introduction to the basic operations of a simple computer. And this hardware arrangement is what we refer by the term computer organization. Computer organization is different than computer architecture because it indicates the basic operations and generic components to facilitate the operations. A computer architecture is more advanced. It shows more detail for specific systems and specific application fields. Thank you for watching.